Welcome back, Chemistry 30. The previous video got kind of cut short, but we'll continue here. For balancing a redox reaction that occurs in acidic solutions, because we'll look at basic solutions as well, like we did with the oxidation number method. Here's the process. So we divide the equation into one oxidation half reaction and one reduction half reaction. So it should be pretty easy to see what's being oxidized, what's being reduced. You could go through and assign oxidation numbers, but it'll be pretty obvious. Balance each half reaction. So first balance anything that isn't H or O, and then balance O's by adding H2O as needed, then balance the H's by adding H pluses as needed. Finally, balance charges by adding electrons to either side. So those are the key steps right there, actually, the initial parts. So balance other atoms, then balance the O's, very similar to what we did before. Balance H's by adding hydrogen ions to each side, and then whatever side is short of electrons, because remember, we're allowed to add electrons to either side. We're not allowed to take away, add electrons, and then it should be balanced. This specific sequence is important, and it's summarized in that diagram up there. At this point, you can check whether the number of electrons in each half reaction corresponds to changes in oxidation state. Then we'll have two reactions, right? One will be oxidized, one will be reduced. Multiply half reactions by integers to make the number of electrons lost equal to the number of electrons gained. So that's a key thing. Multiply to get the oxidation half reaction electrons equal to the electrons in the reduction reaction. Then add the half reactions. If we can cancel things out that appear on both sides of the equations, we can do that. And then check to make sure the atoms and charges are balanced. Okay? So it seems like quite a few steps, but as you see, as we go through examples, it's not too bad. As an example, let's consider the reaction between the permanganate ion and the oxalate ion in acidic solution. When MnO4 is added to an acidified solution of C2O4, 2 negative, there's the deep purple that the MnO4 has. It fades, bubbles of CO2 form, and the solution takes on a pink color of magnesium ions. We can therefore write the skeleton equation as this. So if we wanted to, we don't have to do this step, but what we could do is figure out, okay, we could figure out what is being oxidized, what's being reduced by doing what we did before. So -8, -2, so this has to be a +6, which means that's +3. So what we did before, but again, we don't have to do this. -2, -4, this needs to add up to be 0, so we have that. So we can see here the MnO4 is going from +7 to +2, so obviously it's getting reduced, an oxidation number change of +5, and carbon is going from 3 to 4, so it's getting more positive, so it's being oxidized, it's changing by +1. Okay, so at least this tells us what substance is being reduced, what's being oxidized. So it's the Mn and the C that are undergoing changes. Experiments show that H plus is consumed and H2O is produced in the reaction. Okay, so we can go from there and then see what's going to happen. So we see that their involvement in the reaction is deduced in the course of balancing in the equation. To complete and balance the above equation using the half reaction method, we first write the two half reactions. Step 1, one half reaction must have the Mn on both sides of the arrow, and the other one must have C. So we know that Mn going to this Mn needs to be one reaction, and this C going to this C needs to be the other reaction. So the first reaction is this, second reaction is this, because we know Mn is undergoing a change, and we know C is undergoing a change. All right? So if we go with that, so we did that, we divided them into two half reactions. Now we need to balance the elements that aren't H or O. So we'll start off with this one here. So MnO4 going to Mn. Let's just read this first. We next complete the balance of half reaction. First we balance all elements except H and O, as I mentioned. In the permanganate half reaction, we have one magnesium atom on one side of the equation and the same on the other, so we don't need to do anything here. But in the second one, we have two C's going to one C, so we have to put a 2 in front of that C to make it work. Okay? Next, we balance the O's. So what we'll do is we'll grab this reaction first, work with that one, because the next step is balance the O's, balance the H's, and then balance the charges on each side by adding electrons as needed. So we'll take a look at how that works. So MnO4, so we can see here that we have Mn's are balanced, but we have 4 oxygens on the left, none on the right. So we need to have 4 oxygens added to the right, and we add oxygens by adding water molecules. So we add 4 H2Os. Okay, so balance the O's by adding H2Os as needed. So that's what you have to remember. You balance oxygens by adding water. Then of course you're going to have extra H's on that side. So you balance H atoms by adding hydrogen ions to the opposite side. So if I have, let's see here, 4 groups of 2, that's a total of 8 hydrogens. So I need to add 8 hydrogens here. So as you can see, I have 8 H's, 8 H's, 1 Mn, 1 Mn, 4 O's, 4 O's. So it's balanced. So the next thing I do is I need to figure out the total charges on each side and add electrons where I need. So if I look over here, here I have some positives, right? I have positives, and I have 8 of them. Over here, I have a -1. And since I have 1 of the molecules, I have 1. So that's going to give me a total charge of 8 positives. 8 minus 1 plus 7. On this side, I have 2 positive charge because there's only 1 Mn here. Here, the charge of H2O is 0. I have 4 H2Os. So that's going to give me a total of 2 positives. Okay? So that's what I'm showing over here. So the charge of the reactants is 7 plus. Doesn't really matter what side you write that on, and the product, of course, is 2 plus. Now I'm allowed to add electrons to one side. So the key thing here, add electrons to the more positive side, because you want to bring it down to the negative side. Bring it down to the dark side. So to make this side match this side, the side that's more positive is over here. So if I add 5 electrons, 7 minus 5 will give me plus 2. I will have equal charges. So the key thing here is that to balance the charge, to balance the charges on each side, you add electrons. So then you add electrons to the more positive side. So add it to the, so if I do that, then you can see I will have an equal number of charges because I'm adding 5 negatives to the plus 7 side, so that'll be plus 2, and both sides will be equal. So on the next page here, we can use oxidation states to check the results. On this half reaction, Mn goes from plus 2 to the plus 2, therefore each Mn must gain 5 electrons. And we saw that when we did that earlier. If you look at the other reaction, the oxidation reaction. So we had, this is what we came up with in terms of electrons. So if we balance the charge by adding 2 electrons to the product. So this one was kind of easier because we didn't have to worry about anything else. So over here, remember we had to add oxygens to water to make the oxygens the same? Well, this one, we had 4 oxygens, 4 oxygens, 2 Cs, 2 Cs. So we didn't have to add oxygen by adding water. Because we didn't have to add water, we didn't have to worry about H's. So all we had to do is worry about charges then. So on this one, we have a 2 negative charge, and we only have 1 of these compounds. So that's a total of 2 negatives. On this side, there's no charge. So if we have 2 of them, that results in 0. So of course, to balance the charges, we need to add 2 electrons over here. 2 negatives, it equals. So yeah, we could skip. We skipped all those steps there with the second one because we didn't have to worry about oxygens that weren't balanced, and then because we didn't have to add water, we didn't have to add H's, so it's a little bit easier doing that one. So if we go back to here, so we have that. We can check the results by adding the oxidation state. So yes, if we wrote down the oxidation numbers, we would see that that works. Now now over here, so we added 2 electrons. So we have 2 electrons added there. And on the previous one, we had 5 electrons. So the lowest common multiple of 5 and 2 is 10. So we're going to have to multiply this equation by 2, multiply this equation by 5 to get 10 electrons and 10 electrons. So that's all we did here. So that first equation, I just simply multiplied everything by 5, or sorry, by 2. And in this one, if I multiply by 5 to get 10, I'm going to have 5 of these. 5 times 2 is 10, and 10. 5, 10, 10. Okay? So that's what we had to do in order to get that. And so things that cancel, so we have 10 electrons here on the left, 10 electrons on the right cancel out. I don't think there's anything else we can cancel out. So we'll write out all the reactants. So anything that's on the left-hand side of the arrow, boom, 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 there they are. Then the other side of the arrow, boom, 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 there it is right there, and that is balanced. So the balanced equation is the sum of both of those half reactions. Note that the electrons on the reactant and product sides cancel each other out. So yes, we cancel out the electrons when all is said and done, because electrons help us to get the right number of species, and then they can cancel. And then I can check by counting the atoms. So 16 H's, 16 H's, 2 Mn's, 2 Mn's, 10 C's, 10 C's. And over here we have 20 O's plus 8, so we have 28 O's. And over here we have 10 times 2 is 20, 28 O's. And the charges should work out as well too. So we have 16 1 positives. Here we have 2 negative 1s. Here we have 5 2 negatives. So that's going to give us negative 10 and a negative 2, which is negative 12 plus 16, so that's 4 positives. Over here we have 2 positives, 8 no charges, 10 no charges, so 0, 0, look at that, 4 positives. So the number of each element in the compound is the same, and the number of charges are the same. So plus 4, so that is correctly balanced. Okay, so we'll stop there, we'll come back, and we'll do a couple of examples with this.